Yeah, so I'll present our work on checking beliefs in these dynamic networks. And this is joint work with Nikolaj, Bjørner, Patrice, Godefroid, Karthick, Jayaraman, and Varghese. So networks don't need any introduction here, but let me just highlight some points that motivate our work. First is that networks are business critical and complex. And this means that we are going to have expressive bugs, because if they are complex, it means that they are going to have bugs, right? And if they are business critical, well, if something fails, it's going to be expensive. And second, in these data centers, since they are a closed world, we have fast protocol deployments. So we see a lot of protocol changes, and these are quite frequent. And finally, there's a lot of legacy to maintain. So we have networks, we are like 20, 30, and more years old. And it means that network operators don't usually have the full picture of what's going on in your network. And so this is where network verification comes in. So the goals are so we want to identify bugs. We want to identify beliefs that are not exactly current from network operators. And overall, we want to increase confidence, that the network is doing the right thing. So the previous two talks were also on, some sort of network verification. So let me just point out what the differences are regarding this paper to the others. So the last talk was, on the implementation of the network protocols, like protocol conformance. And the first talk was on the routing configuration errors at the control plane level, and this talk will focus on the data plane level. So in comparison with other data plane verification tools, we see that there are these two sides of speed and expressivity. So on the speed side, we have these really fast tools, such as ASL, Veriflow, NetPlumber, that are specific for data plane verification, and they're really fast. On the expressivity side, we have these traditional tools like model checkers and SAT solvers, which are more general, but they usually don't perform very well in this domain. And we position ourselves in somehow in between, and we call this the Network Optimized Datalog, or NOD for short. Okay, but why do we care about expressiveness? First, at the network level, so it enables us to model these dynamic behaviors. So we can model, new packet headers or new forwarding behaviors without changing the tool. So previous networking verification tools, usually they are tied to a particular forwarding behavior, and if you want to add, say, a new packet header, you need to change the tool's internals. And the second is at the specification level. So we want to be able to specify, these higher level beliefs, such as, all backup routers are equivalent. And some of the previous networking data plane verification tools, so these specifications were baked in the tool. And here we take these as input. Okay, so since we are talking about beliefs, let me just briefly show a few examples that we have considered. So in the paper, we go over these 5 templates that we have identified. And for example, this middle box template says that, for example, if I have a path from A to B, then the set of middle boxes that I traverse, that I go from A to B, should be roughly the same as when I go to B to A. Okay? And we actually found that this was a real problem in some of our networks. Okay, so I've just motivated the problem. So let me just show, how we solve it. So we have this network optimized datalog, or NOD for short. The idea is that we use datalog for the input of both, data plane or the control plane specification and the verification properties. And then we have a tool for efficient verification of data planes that are given in this language. And this tool is available in this open source SMT solver named Z3. And Z3 is a widely used solver for software verification. So we leverage all the goodiness that is already there, all the years of investment, and then we improve it to scale to this domain. So why Datalog? We argue that it has this a good expressiveness and efficiency trade-off, and in particular, we are able to support, for example, packet rewriting and load balancing, and not all the previous data plane verification tools supported this. And second, it provides all solutions for free, unlike SAT solvers. And what this means that, for example, if you use a SAT solver and it finds a problem in your network, it will basically get a very specific packet that says, well, if I have this specific source IP, this specific destination IP, then something will go wrong. But we found that it's more intuitive if you say, well, if I have a packet with this IP prefix and it goes through this path, then something wrong will happen. So it's easier for network operators to debug what's the problem. Okay, so how do you model networks using Datalog? So it's quite straightforward. So the idea is that each matching rule, saying the fibs or echoes, become one Datalog rule, and the state that we propagate is what's the set of packets at each router at a time, and then we do the fixed point over these programs, and the final result is a set of packets at some location. So the encoding actually does matter. So I don't have time to discuss here exactly what's the best encoding, but in the paper we give more details on why some encodings are not as good as others. Okay, so it seems that Datalog is perfect, but so what's wrong with it? And the problem is, so out-of-the-box implementations out there are quite slow for this domain. And the reason is that they will process one packet at a time. And in these networks, we have 2 to the power of, a lot of packets. So it's unreasonable to do, one packet at a time. So our contributions is that, so we use a symbolic representation for packets. So we deal with sets of packets instead of one packet at a time. And we implement a more efficient propagation of these packets across routers. So in terms of representation, we use what we call difference of cubes, which was used in HSA already, but we generalize it to a more general setting. So, for example, we support negation, which is necessary, for example, to check consistency across backup routers or load balancers, which HSA cannot do. And more formally, it looks like this. So if you have VI, VJ, which are ternary bit vectors, so they can have like 0, 1, and don't care. So it looks something like this. And I have some examples. So here are 2 examples of sets of packets that would be at some router location. And this representation is quite efficient for this domain because it has this negation and is very efficient for rule dependencies in echoes, for example. Okay, so our second contribution is fusing internal Datalog operators. So Datalog is traditionally from the database community, so it's not surprising that most tools implemented using relational algebra. And the idea is that some of these operators are not efficient for this particular domain. So let me give you a quick example. So imagine that we have a router that is dropping HTTP packets, and and the input for this router is all packets that start with 1. And let's assume that packets only have 3 bits for now. So the first thing that this Datalog engines will do is, so the input is represented as a table of 1 star star, okay? And the second step that we're going to do is to join this table with a full table to create an input-output relation. That's the join. And then in the select, we'll constrain this input-output relation to what happens, so which is like dropping HTTP packets. And finally, since we don't care about this I/O relation, we just project out the input and we get the output, which is the final result that we want, which is what are the packets that get out of this router. And this intermediate result from the select is not efficiently representable in this representation. And so what we do, we go directly from the join to the project, use the fused operator. So for those of you that know about program analysis, this is basically computing the strongest postcondition or quantifier elimination. So this technique is also more applicable. Is also applicable to software verification. Okay, so let me show you some results. So we asked ourselves a few questions, which were like, do these beliefs actually help? And how hard is to add a new forwarding protocol, since we are claiming that we are more expressive, so does this actually hold? And how do we perform in terms of speed compared to other data plane verification tools? And is any of these useful in practice? Hopefully, yes. So, okay, so first we took this locality belief. And the idea, so here I have a picture from our data center. So this network is very hierarchical. So if I send a packet to my neighbor rack, so I don't want the packet to go to the internet and come back. So we check that this belief that packets should not go too far actually holds. And I have a table here on the right. So these are results for the Hong Kong data center for 3 different clusters. And we have the time in seconds for different types of queries. So the first line is traffic between 2 clusters. So we are checking whether, if I send traffic from one cluster to the other, that the traffic does not go too far. And it takes about 12 seconds. And the next 4 lines check whether traffic coming from the internet to some specific service inside of the data center go to the specific data center spine or the cluster spine. And it's also done in a matter of seconds. And we found multiple violations of this, obvious belief. And these were possibly caused by either bugs in the wiring during build-out or routing bugs. Okay, second, we took one of our network operators and we tried to check whether his beliefs actually hold in practice. The thing is that, once you have, these millions or hundreds of thousands of VMs, so you cannot really specify these beliefs in terms of reachability from a specific VM to the rest of the world. But these operators do have, higher level beliefs of what should happen, to customer VMs or to internal VMs and things like that. And so we did actually find exceptions to the beliefs of these operators. So one of the beliefs was, customer VMs cannot access Fabric controllers. And we found several exceptions to this belief. But then we actually confirmed that all these exceptions were OK. It's just that the belief of this operator did not include all these possible and tricky exceptions. So this process of refining the beliefs of operators is actually pretty good because it allows you to produce the specification of what the network is actually doing. So in terms of dynamism, So we took a MPLS-like backbone with custom forwarding, and we tried to do data plane verification for this backbone. And it took us only a few hours to model this completely new forwarding behavior with different headers. And then we could do the standard data plane verification queries like loop detection and black hole detection in our tool. And we did not have to do any change to the tool at all. In terms of performance, so we compared Node against model checkers, SMT solvers, and HSA, which is a state-of-the-art data plane verification tool. And what we observe is that Node is faster than model checkers, and model checkers are computing just one solution, and Node is computing all solutions. And Node is still faster in this process. But HSA is faster than Node. However, since it's not as expressive as Node, so it cannot do all the benchmarks. And so we have this trade-off, it's faster, but it cannot do everything. Of course, potentially, HSA could be extended to do all the other benchmarks, but again, you'd need a lot of engineering effort to change the internals of these tools. Okay, so is any of these things actually any useful? And the answer is that we have actually deployed a simplified version of Node in Azure, and it's called SecGuru. And what SecGuru is doing is, the difference to Node is that it performs local checks. So in Node, we usually take the whole network and we perform the analysis on the whole network. And SecGuru looks at one router at a time, and it basically assumes what the rest of the network is doing. So it has this belief of how the network behaves. And then it can get away basically with local checks by looking at one router at a time. And this trick actually works because these data center networks are very structured. So it's reasonable to do these kinds of things. And it's finding about one problem per day right now, worldwide. Another cool thing of SecGuru is that it was used to reduce the corporate echo from 3,000 to 1,000 rules without any outages. So SecGuru was used to prove the equivalence between two configuration files, or actually to show what were the differences, and then the network operators could acknowledge whether this difference would make sense or there were bugs. Okay, so to conclude my talk, basically, so we claim that Node is expressive, and we take as input the protocol specification, which allow us to deal with all these dynamism, with new headers, new forwarding behaviors, and so on. And we also take the verification property as input. So we can express network operators' beliefs without changing the tool. We also claim that we are more expressive than previous verification tools, while still being competitive in speed. Finally, the network operators' beliefs are fragile. So they have a rough idea of what's going on, but usually they don't have the full picture. So tools like these actually help them to understand what's going on. And finally, most of the code on Benchmark is available online. It's open source, so feel free to use it. Okay. Thank you.
Hey, Vyas from Carnegie Mellon. This is really cool stuff. I was thinking back to your Venn diagram with scale and expressivity, and somehow, so you were in a subset of that space, right? Mm-hmm. Can you comment a little bit about sort of what the limitations of Datalog are, just out of curiosity, like what can it not express? I mean, it's more expressive than HSA, but what can it not? Give us an example of what it cannot do.
Okay, so let me go back. So there's one point there, which is Margrave. So Margrave uses first-order logic, so that's more expressive than we are. The thing is that for practical purposes, we didn't find any case where this extra expressivity was actually needed. So, I mean, I don't know exactly what we are losing, but for our tests, we didn't find any case that we did not express. But yeah, but there are tools that are more expressive, and Margrave, I think it's the...
I think I was asking more in terms of sort of from the networking side of things. I mean, I understand first order logic is more expressive in Datalog. I'm asking more from the networking side of things. Have you thought about like what networking scenarios may or may not capture? We can take this offline.
Yeah, I don't know. So I think in practice, I'm not sure that we lose much. That's my intuition.
Hi, it's really great. I really like this work, so really appreciate it here. I got 3 questions, really, and it's kind of out of curiosity. So the first one is about NLD, like language features. So if you look closer in your comparison of your tool and the model checker and SMT solver, so your tool beats model checker both most for its performance, whereas it beats SMT solver because it solves more like it's more expressive. And so I see your language feature in your paper. You have this very impressive feature like negation, non-determinism. So I'm really wondering like what exact negation you're referring here, because negation for Datalog, it's really it's classic problematic problem. Yeah, so can you clarify it a bit? And also I see like negation in your rule. I didn't see any like occurrence in the head of a rule, but it appears in the body of the rule. So like, what's the semantics for negation? Like, is this closed world assumption? If it is, like what kind of like NLI model you really have here? Yeah.
I'm sorry, I think I lost a bit myself. So you were asking about what are the problems with negation somehow?
Yes. Or like how do you define negation in your framework? What's the semantics? What's the interpretation?
Okay, so Datalog doesn't have a general negation. So
exactly.
Usually Datalog you have to have a stratified negation,
yes.
right? And our current implementation only supports stratified negation.
Okay.
We are actually working on extending Z3 to support things like aggregation over monotonic predicates only. But for example, tools like, so there are other Datalog solvers that support non-stratified negation. We chose not to support it because we didn't have any case where it was actually needed. But yeah, but it might be needed, but we didn't come to any test case where it was actually needed.
Sure. So how about non-determinism? So it's really wondering. Or we can discuss this offline. And a second question is about, I see, the evaluation engine of your framework, you have this slide in your paper saying that you're translating your language into relational algebra. So I'm really curious, so if you are translating this into relational algebra, then why not using a relational, say, database query engine, like out of the box, like Postgres?
So your question is, why don't we use a SQL server? Or,
yes, if you are translating it into SQL anyway.
So the difference is that we use relational algebra, but over symbolic representation. So you can think that it's like a database, but instead of having, concrete like rows with numbers, we have rows with like formulas. So, and you cannot, like, since the set of packets is really huge, so we have like billions of possible packets. I mean, if you were using a SQL database, you would have like billions of rows in this table, so it would not scale, basically.
I see. So my last question is actually related.
Let's let the other question ask it.
But we can chat offline more. Yeah, sorry.
Hi. So, could you pull up the performance numbers compared to the other tools again?
You mean this?
Yeah. So, for the performance comparison, so in the top row, we see that SMT all solutions takes 0.1 second compared to not SMT solver, I assume, being more expressive, right?
SMT solver is more expressive, yes. So that 0.1, I mean, so the solver got really lucky because.
Okay.
So I mean, because if you see the next row, I mean, it's pretty bad, right? The thing is that since the first test case is unreachable. So being all solutions or being one solution, it's the same, right? Because you only have one solution, which is no.
Yeah.
And that's why the second row is way worse.
So it doesn't have to enumerate anything,
yeah,
really?
exactly.
Okay.
That's why, it's pretty fast, but it was also lucky. So in these things, so the reason is that, so in SMT you have to unroll the network, so you have to do like bounded enrollings. And here for this test case, it gets rejected on the first unrolling. So the test case is really simple for SMT solvers, basically. That's the reason.
I see. Thank you.
All right, let's thank Nuno. This concludes the session.